Thank you for being here. Thank you for having me. So my name is Aurélien. I have 20 plus years experience, mostly around optimizing operations for big projects, very widely optimizing operations, project management, and making sure that added value time of the people is well spent and not on tasks that can be automated, broadly speaking. So my talk is going to be about industrializing continuous learning. By that, I mean retraining continuously models so they get better and better. And it's mostly an industry use case. It's for companies. So they retrain the model in newer data they get as time goes by. And so during my presentation, I will be using a running example to illustrate what I'm going to talk about. So it's going to be very illustrative. And the use case I'm going to be using is going to be around an LLM specialized in function calling. So we're going to see how we can make a very good small LLM, very good at being an expert at function calling with retraining. We will see that in detail. So my talk is going to be split in 4 sections. The first of which is going to be about the retraining framework we are going to use for this. The second section is going to be a refresher on what exactly is function calling, how does that work under the hood, what's happening. The third section is going to be the start of the illustrative use case. So I will, as I said, use a running example to showcase how we can continuously retrain an LLM. And the third, the last section, the fourth, is going to be about serving our expert LLM in function calling and making sure it fits well, it can integrate in any IT team, IT environment, IT ecosystem. So it's going to be inference as a service. So let's start the first section about the retraining framework. So I'm basically the main author of the framework I'm going to be talking about. And the idea behind having a new framework, having a new tool, is that I feel like in MLOps, in industrializing machine learning in general, people think of tools as a way to automate, but they just think of it that way. And I think it's important to also include some kind of ease of use and confidence and feeling of naturality for the users. So the tool is not just about automating, but it's about making people having less moral burden, less weight on their shoulder. They don't have to think about lots of things. It's done under the hood, and it feels natural to use it. So I will go in details on how I think I implemented it. Also one of the main differentiator of that pipeline, of that package, so I didn't even mention it, but it's named Retrain Pipelines, it's open source. So one of the big differentiator is that it's pip installable. In that sense that you don't need to install separately a database, install separately a web server. It's just pip install and you get all installed in one location. And of course, it does come with sample pipelines. So that's another big differentiator. I have developed, and it's a library, a directory under the GitHub repo, which is it's being maintained heavily. So I add new sample pipelines every once in a while. It's to illustrate different use cases and how it can be employed out of the box and customized to your different needs. So additional big differentiator of the retrain pipelines as opposed to existing MLOps platforms that are out there is that it does implement stuff that are very specific to machine learning, which are, for instance, model version blessing. And by that, I mean you evaluate the performance of newly retrained model version and you compare it against that of the best predecessor. And if it's not performing better, then you don't deploy it. So it's part of the package. Another specific of the package is what I call infrastructure validation. So basically, when you execute a retraining pipeline, one of the last tasks that is being performed consists in packaging and deploying the inference service in an isolated Docker container. And part of the retraining pipeline, we send an inference request to that service, and we make sure that the response is correctly formatted. And the idea behind that is that consumer of that service is not going to be broken if you upgrade the model, if you retrain it. Before releasing anything, we make sure it doesn't break the interfaces. And yet another big differentiator of retraining pipelines is that for each execution of retraining pipeline, it does generate what I call a pipeline card. I guess by now people know of model cards. It's metadata related to a model. And so I extended that concept to pipeline card, and it's basically metadata pertaining to all the tasks end-to-end of a retraining pipeline. But we will see examples. Yeah, and again, the idea behind that is so people they can focus on what matters to them, the ML engineers, the users of the package, meaning focusing on data quality, data curation, and model performance optimization. So yeah, for instance, you can use that package from wherever you like to work. Like for instance, there is a nice notebook cell magic in here. So you can launch it from a notebook if you like. By that I mean launch the execution of a retraining pipeline. Or you can use the CLI utility in here directly from your favorite terminal. Or you can even, launch it programmatically. For instance, here in Python, there is a dedicated method to launch the pipeline from within Python script. So you can think of cron job, scheduling, whatever. So yeah, another big part of what makes the DNA of retraining pipeline is that it does integrate its own internal DAG engine. And the idea is really to make it as simple as possible to develop and maintain retraining pipelines. So basically, it's a set of a pipeline. You can think of it as a set of Python methods that are being decorated, and the last method represents the pipeline itself, where it's about chaining the methods, chaining the tasks. In here, it's basic chaining. So, and it's not just tasks, but I also introduced the concept of task groups, where you can, so a task group is just a set of tasks that take all the same, they take the same input, and they are execute asynchronously, and the successor task gets the output from all these tasks, from within the task group. So again, it's just declaring the set of tasks that are part of a group, as we can see here. And there is also the concept of subdag. So it's basically parallel execution of slices of an input data. So basically, you pass as an input of a parallel task, as we see here. You pass it an iterator, and then it just launches parallel subdags, each taking one of the records of that iterator. Yeah, and so what makes the end of a subdag, of course, is a merging task. And as we can see here, it takes a merge function to aggregate the results from the subdags, the different parallel distributed subdags. Yeah, and so we can also declare custom aggregate function, like in here, for instance. Just to illustrate, you can develop and declare your own merging functions. And last for this slide about the internal DAG engine. I also implemented different functionalities so that, and we will see it in the next slide, in the web console, the DAG, they are rendered with tasks, with specific, optionally specific CSS styling, like border colors and background. So basically, it's in here, you can declare for a task some kind of, how it renders in the DAG, in the web console. And also, the doc strings for the different methods, like in here, these doc strings, they are also displayed inside the web console. So when you document something, it's not just the code that is being documented, but also you have the information in the UI. That's a short video about the UI. Okay, the mouse is not working. Okay, so you can filter, and you see the DAGs have their own formatting, so that when you look for one only, you're very familiar. You cannot confuse your different DAGs, so that there are different executions of the same DAG. You have the doc string from the DAG showing. You have the doc string for the task groups. You have the doc string for the unitary tasks. You have autocomplete for the search. You can filter by execution success status. And we see here that even at the task level, you have the custom formatting. We will see how it can become ND in a few moments. It's not just about aesthetics. And you have the name of the custom merging function. And you have whether or not there have been failed executions historically. And of course, it's reactive to external events. So if there is a pipeline execution launched, so it appears here until it completes, and it's dynamic. So that was for the web console. And the intent behind all that is that we've seen 2 slides before, prior to this one, that we can declare all tasks within the same module. But the intent is, of course, for companies to develop libraries, internal libraries of tasks for them to be reused. So be imported, when you declare a DAG, you import your tasks. Like for instance, in here, we are imported a theoretical task that is called inline, and we can declare and use it in different pipelines, and that's how it would show. So when different pipelines are using the same task, it shows here visually, so it's easy to see this is the same task, for instance. So now we will see examples of the concept behind pipeline cards. So the idea for pipeline cards is that they are portable, self-portable HTML file. So you can export them, you can expose them with a serving server, with an inference server. You can have an endpoint for document, for instance, and have the complete trace of how this retraining went based on what data and everything. But we will see examples. So for instance, here. So that's one example of retraining pipeline. The first important version is that model version was not better performing than its predecessor. And if we want to visualize the predecessor's retraining pipeline, we can click here. But that's not the point. So we have a section on EDA. So that retraining pipeline, that model version was trained on that data set with this information. Again, all that is fully customizable. It's a sample pipeline to illustrate, to give ideas to ML engineers so on how they can go. You have a section on the training execution. And inside the section training execution, we have also sliced performance reports on the slice dataset, and we have also, again, optionally, a section on hyperparameter tuning. So if you have distributed parallel tasks about hyperparameter tuning, you have the nice plotty charts that can be integrated as well. And there are also sections. I'm not going to detail further. But one of which, so the next section is a list of Python commands that, if executed locally on your terminal, give you access to the model weights, any artifact of interest. And there is, of course, inside the pipeline card, the DAG rendering that we have seen before. So retrain pipelines, it also does come with third-party integrations. There is a third-party integration for weights and biases, for instance, and I will show you here in more details the third-party integration with the Hugging Face hub, and basically it allows you to have the Hugging Face hub serve as your artifacts store. So let's look at one example. So this example is from the use case I'm going to be detailing in the next section of my talk. It's about function calling. It uses that third-party integration, and basically what it does, when the pipeline executes, it not only publishes the dataset and the model, but it publishes also this model card, which itself references pages such as this one. When we also publish the training code, the version training code, and all the dependencies, anything necessary to reproduce that execution. So it's just the same implementation of MLOps principles, and we also publish the pipeline card in Hugging Face. Opening right now. Yeah, so that's basically the pipeline card for the example I'm going to be discussing in further detail in a moment. But you have the EDA section, you have the training execution section with the CPT loss curve, the SFT loss curve. We will see details about that, but also the performance chart that I will also be detailing in a moment. And of course, you have the artifacts section and the DAG section in the pipeline itself. Let me, something I didn't mention. Okay, so in the model card itself, you have also the lineage information about the version of the dataset that has been used, and also we will be discussing this in detail for this sample pipeline, but it is using a base model as a starting point, and so basically you have also the version of the base model that is mentioned in the pipeline card itself, in the model card itself, so it's full lineage also that is automatically logged every time you execute the retraining pipeline. Good. Moving back to the slides. Yes. Yeah, and one more thing that comes nicely with retrain pipelines out of the box, part of the package, is there are a set of inspectors. So basically, the concept of inspector is for if one day you're interested in digging deeper into one particular execution, for instance, if you're interested, if it's highly distributed and you want to see why what happened on a particular worker or something like that, there are inspectors for that out of the box in the pipeline, in the package, retrain pipeline package. And another sort of inspectors that are also included, I will talk to you about the Hugging Face integration. So inspector in relation to Hugging Face integration, so if you don't mind the import lines, it's just 3 lines of code that allow us to inspect everything in relation to the version history of the given model, given its repo ID. So if we see here, the only parameter is the repo ID, and if it's private repo, you can also inform your token. And so you call here, and what it does behind the wheel is it retrieves all the metadata from Hugging Face, and then we have one call that allows, we will see it in the next slide, it will here render a nice HTML table about the history of revisions. And here it allows to show the same data as a chart. So moving to it now. So this table rendering, it's a sorted list of different model versions with in here in the second column it's direct link to the Hugging Face model repo for these versions. So again, for each of them, you click on it and you open the page I've shown you in relation to that version. So with full lineage and everything, pipeline card, you name it. So that's the HTML format for the table. And the second command allows to draw that chart. So basically, it's an easy way to see which model version was better to his best predecessor. So for instance, this one was not worth publishing when this was. So that's for the inspectors. So yeah, I spent quite some time on explaining the retraining framework. These sections are shorter. So this first of the three sections is a refresher of how tool calling works. So let's get there. So yeah, so there is a mistake in that slide. I will show you which, but there is a fault. So basically, the workflow. What happens when a model uses tool call? What does it mean when we say a model is good at tool calling? What does it mean? So there is a query, a user query. Our example here is the user asks, is 48 a perfect square? The answer to that is no. But so that user query is appended to a list of tools that are available to the LLM for him to pick. So basically it's made up of the name of each tool. So here it's two tools. The first one, the second one. So the name of the tool, a description of what the tool does, a description of the different parameters and type of parameters expected for that tool. So all that, for each query, you don't just send a user query to the LLM, you send all that for all the tools that are available to it. So it's an extended context. So you send that to the LLM. And then the LLM, what it does is that it infers this suite of tokens which represents this string. So basically, when an LLM does tool calling, it just infers this string, which is then passed to a sandbox environment where you do import your library of tools, and you make the call. And that's where there is a mistake in this slide. Of course, the answer is false. So this is what happens. It's not in relation to the LLM. And then next step is the user query plus the response from the tool call, which is false. They are appended to each other, and then they are sent back to the LLM, and the LLM is then in charge to formulate a nice answer to the users. So typically, is 48 perfect square? The final answer is going to be, no, it's not. This is a processed response by the LLM. So we have two calls to the LLMs, two inferences. So first of which is a task of tool calling identification. And the second task is the task of an instruct model, basically just formulating responses to questions. So yeah, it was the workflow. And now I wanted to also show how it looks when we use the completion API, the famous. So basically, yeah, you declare the tools as Python methods. Then you further indicate what the tool does. That's the same as what I have shown earlier, but here it's Python code. That's basically how you do it. So you declare the tools here, and then you give it the description, what does that tool do, and then you give it the typing of the signature of the method, and all that. You also add the user query, of course. You send all that to the completion API, and that's how it looks. So basically, for each query, again, it's not just a user query that is sent, but also the list of available tools. And overall, in general, it's around 12 tools. And there is a hard limit, I believe, on Cursor, for instance, to up to 50 tools, but it never goes higher. So it's fairly limited amount of tools. So that's for the completion API. And the newest responses API is very similar looking. If I switch between the two back and forth, we see the differences are very limited. And actually the differences with the responses API is in the format of the response object that is being returned. But that's not very important to our subject here. Okay. So that's tool coding, how it works, what does it mean? And now, I'm going to spend a couple minutes on explaining how to evaluate the performances of a model with regard to his capabilities in relation to tool coding. So basically, there are many ways to measure it. So Berkeley Function Calling Leaderboard is a very recognized, highly recognized benchmark with regard to comparing models between each other regarding their capabilities in function calling. So this is an extract, very recent, end of August this year. It's a lot of huge models, and what matters is that overall the performances, they are not that great when you look at the numbers. So we will be focusing on that column. So that column is singleton, meaning that's the example I gave earlier. One user query, no chat history, just one user query and a set of tools. And so that's singleton. And non-live is that we do not send the user query to a sandbox to check that the return is correct. We just check that the tool call generated by the first LLM is the right one, appropriate. So yeah, again, we see the numbers here. So it's for the very best of them all. It's 88%. It's good, but there's still room for improvement. Okay, so we went over the retraining framework, a small reminder of what tool coding is, and now we will go over this use case for enterprise-grade retraining of function coding expert. And more precisely, we will go with a LoRA adapter. So the idea behind that is that we want to have plenty of experts on a small LLM. Because when you're a company and you're trying to be smart operationally speaking, you don't want to go with a very expensive API with a very big model, or you don't want to self-host a very big model either. You'd rather self-host a small model and have the capability to give it punctually, on demand, extra expertise in some domain. So we are going to discuss having extra expertise on function calling. And not only that, but also we sort of getting rid of the limitation on how many tools can be informed at each request. So what we're going to do, we're going to give our model with this adapter the knowledge, intrinsic knowledge of a tools bank of 4,200 tools. So we send a user query, and the model, we don't send it a list of tools, it knows it from the training, and he first the tools calls to be operated. So yeah, how do we do that? So that's the high-level architecture of an LLM that follows the transformer architecture. So we have three main blocks: the embedding layer, the LM heads, and in here we have transformer blocks. So here there is just one represented, but in general it's a succession of several. And so for the example of the base model we have used, which was Qwen 2.5, 1.5 billion, so a very small model, it's 24 such transformer blocks that are stacked. So that's the architecture of the transformer model, and the LoRA adapter, it applies to different of the matrices of that model, of that architecture. So basically, when you want to teach a task, specialization, you usually do supervised fine-tuning on these blocks. And if you want to add, if you want to go with continuous pre-training, if you want to give your model, your base model, some additional knowledge, you do that by also applying training on these blocks. So we're going to do that. We're going to train in two stages. First stage, continuous pre-training, where we're going to teach our model about our tools bank of 4,200 tools. And the second step is going to be supervised fine-tuning, where we're going to teach our base model how to execute the task of function calling. Yeah, so again, an on-off activable, desactivable adapter. So how do we achieve that? So a few words on the training data set. There's going to be 2 slides on that, actually. I think I'm not too late. Okay, I have to speed up. So basically, function calling data sets are made up of 3 attributes: a user query, a list of tools that are available for that query, and the list of actionable tool calls for that query. So what we do for CPT, we extract from such a publicly available data set, we extract all the distinct definition of tools. That's going to be CPT. It's going to be unsupervised training. We're just going to feed the model unsupervised way the definition of the tools we want him to learn from in our company tools, APIs and everything. And during CPT, what we're going to do, we're going to teach the model user query and inferred tool call, but we will skip the step with we will not feed it with a tool definition per user query. It will have to rely on his intrinsic knowledge. So if we do that, the model is still up for hallucination. So we will also need to teach the model that there are occurrences that are no tool call material. So to do that, that's where we were so far. To do that, we use data augmentation and data enrichment. So basically, data augmentation, we take user queries from the initial data set and we cut in half the queries. So for instance, for the case is 48 perfect square, we can go with is 48 and drop the end of the sentence, and we put that in the training data set. Is 48 is associated to no tool call, so that the model learns that sometimes it might look familiar to him, but it's not a legitimate tool call. It doesn't have all the information. So that's one way to avoid hallucination. And the other is to go with data enrichment. Basically, we take a completely unrelated data set and we associate records to empty tool calls. For instance, literature data set, philosophy data set, anything totally unrelated to tool calls. And so the model learns that sometimes there is just no reason to make a tool call. Like for instance, if a user says hello to the LLM, then there is no function call in return. So basically, yeah, the retraining pipeline sample for that use case as a task that is called continuous pre-training, and basically we are using high-level API. Here it's unslot, and we inform that we want to train not only the transformer block, but also embedding layer and LM heads, which we don't for supervised fine-tuning, but I will not go further in there. So evaluation. So we see here some user queries. They are in the evaluation set. They can trigger up to 9 or 12 and even 24 tool calls for a single query. Our model is very good at not making any tool call when there is none. And we are measuring the Jacquard IOU performance metric, so that when a tool call is legitimate, it acknowledges that, and when a tool call is not legitimate or badly formatted, it also accounts for it. And so our small model is still performing pretty well, like more than 75%. And what's really incredible here is that it does it, but from intrinsic knowledge of 4,200 tools, and not by giving it with each query a short list of tools. Yeah, so there are also false negatives in how we compute that performance metric value. Like for instance, it is in the true ground truth label. Sometimes it's formatted that way, and the model infers that. Basically, they are both very valid, but we don't measure that as positive in the evaluation metrics, so it underestimates actually the performance of our model. And there are other cases like this one when it's just the same park, but not exactly the same coordinates. So there are plenty of false negative actually. Right. So last part about serving. So as we have seen so far, the idea is really to have a small model to which we teach different expertise with different activable, deactivable adapters. So yeah, one thing that's important is that during SFT, we also inform so that the model learns better the task, a system prompt. And basically, yeah, we're just telling it that he's a tool caller expert and that he has to not make a tool call when there is none that is legitimate. But it's important to know that if you train your model with that, it's better performing during inference when you also use that same system prompt. So we basically save it with a tokenizer so that at inference time we can use it. If we don't, it performs badly. Yeah, so basically what I did also as part of this sample pipeline is I created a toy server for that. And basically what we can do, sorry, I went a little too fast. In here, I call, for this case, I don't activate any adapter. So basically it's the base model that is inferring. And so, yeah, it's just continuing, it's just, yeah, getting the most probable next word. It's not responding to any token. It didn't learn anything. It's just base model. And if I do the same thing, asking the same endpoint, but this time I specify that I want the tool calling expert adapter to be activated. And so when I send the same queries, the model, it performs good. Like when I send the user query is hello there, it does return that there is no tool call associated to that user query. And if I send it is 48 a perfect square, then it does infer the tool call. So again, yeah, the idea is to have on-off switches. Yeah, so to summarize this particular use case, the intent is to be able to periodically retrain your model. If you have new tools available in your company, or if some cool tools are deprecated, it's just 4 hours on a T4 for this model to learn it all with 100,000 records in SFT. So it's fairly efficient. It doesn't cost much. You can do it very often. And your model is an expert in knowing your tools and making calls on it. So yeah, self-hostable, cheap. You don't have any vendor lock-in. Yeah, and you can have many such adapters. One that knows everything about your legal department, one that knows everything about your IT department, and then you have one, you can build very complex agentic systems, but with just one small model in VRAM, and you just switch on off any adapter you want. Yeah, so that's it for the presentation. The first of this QR code in here is a link to a very detailed article on that use case. So if you want to go further in detail, there is plenty more information on how it actually operates. Yeah, thank you very much.
Okay, thank you very much.